Here is a claim that sounds strange the first time you hear it. A matrix is not really a grid of numbers. A matrix is a function, a machine that takes in all of space and moves it somewhere new. In the next few minutes we're going to watch that motion happen, and by the end those little boxes of numbers will feel almost obvious. Let's start with the space itself. This flat plane is where every two-dimensional vector lives. Every point out here can be reached, and the grid is just a way to keep track of how far we've gone in each direction. A single vector is just an arrow from the origin out to some point. Think of it as an instruction: go this far right, then this far up. That's all a vector really is, a recipe for where to end up. Now meet the two most important vectors in the whole plane. The first points 1 unit to the right, and we call it I hat. The second points 1 unit straight up, and we call it J hat. These two are our basis, the fundamental steps that everything else is built from. Here's the key idea. Any vector at all is just some amount of I hat plus some amount of J hat. Our arrow to the point 3, 2 is really 3 steps of I hat stacked with 2 steps of J hat. Coordinates are nothing more than the scaling recipe for these two basis vectors. So now the big question: what happens if we grab the entire plane and move it? Not just one point, but every point at once, dragging the grid along like a sheet of stretchy rubber. This is what a linear transformation does. But we can't allow just any wild deformation. A linear transformation follows 2 rules. Lines that were straight have to stay straight, and the origin has to stay pinned in place. No curving, no bending, no sliding the whole plane off center. There's a beautiful consequence of those rules. Because the grid lines stay straight, parallel, and evenly spaced, you only need to know one thing to predict everything. You just need to know where I hat and J hat end up. Track those two, and the entire infinite plane comes along for free. Let's watch it happen. We'll apply a transformation, and I want you to keep your eyes locked on I hat. Right now it points 1 unit to the right. Watch where it lands. And there it goes. After the transformation, I hat has landed at a new location, say 1 to the right and 1 up. That new landing point is the first crucial number we need. Now let's do the same for J hat. J hat started pointing straight up. Watch it swing over to its new home. Wherever it lands is the second piece of information, and together these two landing spots completely define the motion. Now here is where the matrix finally appears. Take where I hat landed and write it as the first column. Take where J hat landed and write it as the second column. That's it. A matrix is just a record of where your basis vectors go. Read that again, because it's the whole secret. The first column is the destination of I hat. The second column is the destination of J hat. Those columns of numbers were never abstract, they were addresses all along. So how do you transform any other vector? You use that same recipe from before. Our vector was 3 I hats plus 2 J hats. So after the move it becomes 3 of the new I hat plus 2 of the new J hat. The scaling recipe stays the same, only the ingredients moved. That single idea is exactly what matrix times vector multiplication is computing. When you multiply a matrix by a vector, you are just scaling the columns by the vector's coordinates and adding them up. The arithmetic you may have memorized is secretly this picture. Let's build intuition with real examples. Here's a pure rotation. I hat and J hat both swing around the origin by the same angle, staying at right angles to each other. The grid spins like a record, and nothing gets stretched. Now a pure stretch. I hat gets pulled out to twice its length while J hat stays put. The whole plane smears horizontally, and every horizontal distance doubles while vertical distances hold steady. Here's a shear, my favorite because it looks so strange. J hat tips over to the side while I hat stays anchored. Vertical lines lean into diagonals, like pushing the top of a deck of cards sideways. Straight lines stay straight, but the whole plane slants. And here's a reflection. J hat flips to point downward, and the whole plane mirrors across the horizontal axis. Notice something subtle happened here that didn't happen before. The space got turned inside out. We'll come back to why that matters. Each of those very different motions was captured by nothing more than 4 numbers. Rotation, stretch, shear, reflection, all just different landing spots for 2 little arrows. The matrix is the compact fingerprint of the motion. Now let's raise the stakes. What if we want to do two transformations, one after another? First, rotate the plane, and then, on top of that, apply a shear. This is where things get genuinely powerful. We just did two separate steps, but the combined effect, rotate then shear, is itself a single linear transformation of the plane, so it must have its own matrix. The question is, how do we find it from the two we started with? Here's the trick, and it's the same trick as always. Just follow I hat and J hat through both steps. Send I hat through the rotation, then through the shear, and wherever it finally lands becomes the first column of our answer. Do the same for J hat. The matrix you get from following the basis vectors through both transformations is exactly the product of the two matrices. Matrix multiplication is not some arbitrary rule someone invented. It is the answer to a simple question: what single motion equals doing one transformation and then another? This also explains a fact that trips everyone up. Matrix multiplication is read right to left because the transformation closest to the vector happens first. The order of operations in the picture becomes the order of the matrices on the page. And order really matters. Watch what happens if we shear first and then rotate, instead of the other way around. The final grid is genuinely different. Swapping the order of two transformations usually lands the plane somewhere else entirely. So multiplication is composition. Every product of matrices is really a stack of transformations, applied one after another. A long chain of matrices is just a long sequence of moves that space goes through, step by step. Now let's ask a different kind of question about a transformation. Not just where things go, but how much the space itself gets stretched or squished. For that, we watch areas. Start with the little square built from I hat and J hat, the unit square sitting in the corner of the origin. Its area is exactly 1. This square is going to be our measuring stick. Now apply a transformation and watch that square. It gets pushed into a parallelogram, tilted and resized. The shape changed, but the real question is, what happened to the area inside it? Suppose that parallelogram now has area 6. That means the transformation stretched every area by a factor of 6. A region that used to cover 1 unit now covers 6. This single scaling number is called the determinant. And it's not just the unit square. Because the grid stays evenly spaced, the same factor applies to every region in the plane. A blob, a circle, your favorite shape, all of them get their area multiplied by the determinant. It's a global stretch factor for space. Now the most dramatic case. What if the determinant is 0? That means the transformation squashes all of space down onto a single line, or even onto a point. Area gets crushed to nothing, and once you flatten space like that, you can never unflatten it. A 0 determinant is the geometric signature of information being lost. Many different input points get mashed onto the same output, so there's no way to reverse it. That's exactly what it means for a matrix to have no inverse. And remember that reflection from earlier where space got turned inside out. That shows up as a negative determinant. The size of the number still tells you the area scaling, but the minus sign tells you the orientation flipped, like reading the world through a mirror. Let's pause and gather what we have. A matrix moves space. Its columns are where the basis vectors land. Multiplication is composition of motions, and the determinant is how much area gets scaled. 4 ideas, 1 picture. Now let's see where this shows up in the real world. Here is a modern place these transformations live, at the heart of a neural network. Picture some input data, maybe pixels of an image or features of a measurement, laid out as a vector. That vector is a point in space, just like our arrows. A layer of a neural network begins by doing exactly what we've been studying. It multiplies that input vector by a matrix of weights. In other words, the layer takes the input space and stretches, rotates, and shears it into a new arrangement. The whole point of learning is finding the right transformation. Training nudges the numbers in that weight matrix, and every nudge is really nudging where the basis vectors land. The network is searching for a way to move space that pulls the useful patterns apart. Imagine data from 2 categories that are hopelessly tangled together, impossible to separate with a straight cut. A good transformation can pull them apart, sliding one cluster one way and the other cluster the other way, until a simple line could split them. There's a catch, though. On its own, a matrix can only ever do straight line transformations. Stack 100 of them and you still just get one big linear motion. To bend space and handle truly complicated patterns, you need something extra. That something extra is the activation function, a gentle nonlinear bend applied after each matrix. It lets the grid curve, not just tilt. Alternating a linear transformation with a bend, over and over, is what gives deep networks their power to reshape space almost arbitrarily. So a deep network is a long dance. Move space with a matrix, bend it a little, move it again, bend it again, layer after layer. Each matrix is one of the transformations we animated at the very start, just living in a much higher dimensional room. And that's the quiet payoff of thinking visually. The same picture that explained a shear in 2 dimensions is running inside systems that recognize faces and translate languages. The math didn't get harder, it just got bigger. So the next time you see a matrix, don't picture a box of numbers. Picture a plane getting stretched, a grid swinging into place, 2 little arrows landing in new homes. A matrix was never a spreadsheet, it was always a motion. That's the whole story. Columns are destinations, multiplication is composition, the determinant is area scaling, and neural networks are just these motions stacked with bends between them. Sit with the picture for a while and the numbers will never look flat again. If this made it click, subscribe for more visual math.